right. Good morning, everyone. Welcome to day 2 of Physics 313. Can somebody just verify that you can hear me okay? Just a thumbs up on the...
Yeah, I can hear you.
Okay, perfect. Thank you, Michael. Great. Thanks, everybody, for the thumbs up. Hopefully you're making progress on your introductory assignments. Remember, there are 3 things that are coming due, that are due at the end of the day tomorrow. An introductory assignment, which hopefully you found on Blackboard, which is essentially just finding and using the various tools and putting in the secret words that I asked, just so I know that you've been there. Then there's also your pre-lecture for chapter 1, and there's an introductory chapter to the Pearson homework system. So please let me know as soon as possible if you're encountering trouble logging on to any of those systems. I know a lot of you have been doing that, and I think we're getting things resolved. Looks like most of you are getting in. Are there any questions before we get going on the material for the day about tools or technologies or course organization? Hi, Bailey, I see you're unmuted. Oh no, Bailey muted again. Okay. Okay, well then, in that case, why don't we go ahead and jump into today's material? So let me go ahead and share my setup here. Okay, great. So everybody should be seeing my my slides here for chapter 1. And give me 1 second. Okay. Okay, so chapter 1 is about concepts in motion, and there are really a couple goals for this chapter. One is to just sort of start to introduce the problem-solving ideas that we're going to use for the rest of the semester. So this is a summary of the information in chapter 1, but I think this is really critical, right? That this chapter very frequently seems simple or easy, but the ideas and the problem-solving strategies that we're setting up, we're going to use basically for every chapter that we encounter this semester. And they include a couple things. One is to make simplifying assumptions. Now, for different kinds of physical systems that we encounter, we may want to make different kinds of simplifying assumptions and understand why we feel justified in doing those. And we'll work through those, but most physicists, right, when you're solving physics problems, the real world is incredibly complicated. Like any macroscopic physical object that you encounter is made up of billions and billions of, trillions and uncountable numbers of subatomic particles that are all self-interacting. And we don't want to try to describe all of that physics all the time. So we need to be able to look at a system, make simplifying assumptions that allow us to characterize it and describe the physics that we see. In this chapter, we're going to introduce a couple ideas, just how to make, right? And I'm going to stress this over and over again, when you're solving most of the problems, mechanics problems in this class, I recommend trying to draw a diagram, a pictorial representation of what's happening. And then we're also going to work on translating what we see in sort of the pictorial representation into more abstract graphical representations or mathematical representations. And also at the end of this chapter, we're gonna focus on units and significant figures. That's something that, of course, for answers and analysis to make sense, we have to understand what kind of measurements we're making in what units and what the digits that we're conveying mean. Okay, so we're going to start this discussion just by thinking about motion. Now, this is the most critical thing in analyzing a physical system, right? Motion, I'm frequently going to say the term dynamics, things that are moving. If there's no dynamics in a system, if there's no motion, then there's nothing interesting to happen and there's no observation you can make. Even if something is sitting on the table and you're observing it, there's really a lot of dynamics happening, right? In order for that measurement to occur, there's light scattering off of that object and photons traveling from that object to your eye. And there's really a lot of dynamic processes. If there's no dynamics or motion in the universe, you can never encounter other objects. You can never make physical measurements. You can never probe the universe. You can never learn more beyond, what you're made out of, right? So motion and dynamics is key to understanding how the universe and how physics works. So we're going to think about, right, try to break this down in this chapter into just thinking about simple motions that's moving in one direction. And we're going to try to go through these different steps here. We're going to practice looking at some physical system, so maybe a car moving like that, and turn that motion into what we're going to call a motion diagram here, okay, which is this upper picture here where I'm indicating the position of the car with a single point. I'm going to draw vectors on that diagram to indicate the velocity that the car is moving with, and I can draw additional vectors at those points that indicate the acceleration of the car or how its velocity is changing. We're going to practice, right, establishing coordinate systems. Okay, this is critical for understanding what is happening in a system. There has to be a fixed sort of background that the object is moving against, right? Your coordinate system, that you're making measurements with respect to some origin of a coordinate system. And for this chapter, right, we're going to focus on these sort of four simple quantities here: the position of an object, the velocity of an object, the time that's been advancing as we've been watching the motion, and the acceleration. So we're going to use those. And so these 6 steps here: draw a motion diagram, establish a coordinate system, make a sketch, define the symbols that you see in your equation, figure out what the problem is asking for, right? List the unknowns, and then, or list the things that you do know about the problem. For instance, what was given to you in the problem and what are you trying to solve for? And then once all those things are in place, try to attack solving the problem. When we're thinking about analyzing the motion of large objects, right, like things that we encounter in our daily life, I'm talking about things that are large collections of atoms that are macroscopic things that we can hold and touch. We're going to use something that we call the particle model to represent those objects. So like I said, instead of trying to keep track of all of the details of all of the atoms in some object, we're just going to boil them down to a single point. And we'll discuss why that simplification makes sense. And in chapter 12, we'll extend to situations where this doesn't work, but for now, we're going to focus on motions where we can use the particle model. We can represent large objects as just single points in moving through space. Okay. These 3 main physical quantities that we're going to look at today, or start looking at today: position is going to tell us where an object is with respect to some coordinate system that I've chosen. And a related quantity is called the displacement, that's going to show us the change in the position with respect inside of that coordinate system. The velocity is a quantity that tells us the rate at which my position is changing. And we're going to represent position by a vector quantity. And we'll see that here in a second. And acceleration tells us about how the velocity is changing. Okay. So for instance, an object has some acceleration if its speed is changing or its acceleration is changing. So these motion diagrams that we're gonna draw are gonna help us visualize motion. They're gonna be a tool for finding velocities and accelerations. Okay. And an important thing to note here is that when we're looking at these motion diagrams, we're gonna be looking at average velocities and accelerations across some time interval t. Okay. We're gonna come in the next chapters to how to understand instantaneous, right, about the accelerations and the velocities that are happening at an exact moment in time. But for now, these quantities are going to be telling us about, over some time interval that I observe the motion, what is the average velocity and acceleration. Okay, so these are kind of the general ideas that we're going to try to establish as we move through this chapter. And so to start this off, we're going to look at some motion diagrams. Now there's a really cool app that if you guys have either an Android device or an Apple device that has access to the App Store, you can download for free, called Motion Shot, that Sony puts together. And it essentially lets you take a video or a series of images of something that's moving, and as long as you hold still and keep the background fixed, it'll overlay those images to make these kind of motion diagrams. And this is the app that I used for to generate some of the images that we're going to be looking at in the next couple slides, and it's fun to play with. Okay, so here's a picture of my son jumping off of some playground equipment that I used to capture this motion here. And so you can see that there are several images of him overlaid one on top of another, right? So what we're imagining is there's a movie. I basically took a movie and then I cut all of the individual cells of the film strip apart and stacked them on top of each other so we can see them all simultaneously. Okay. And so what I can do now is try to simplify and understand this. Now, because he's in general a rigid body, right? He's extended, like his head is right in this shot, his head is up here and his feet are down here. But you can see that if I look down at his feet are following this kind of motion. His head is following a very similar motion. And if I look at his chest, it's also following a similar kind of path, right? That's because for most, right, he's not doing a lot of rotation. He's a rigid body. All of the atoms in his body are stuck together. So they're all doing their own independent motion, but really that motion is the same for, on average, all of the points on his body. So that's what's going to allow us, right? If we have a rigid body, something that's not squishy, that if I move part of that object, right? Like if I have, right? Like if I have my phone here, if I push on the side of it, the whole thing moves together. And so that means I can reduce that object and just think of it as a single point. And what I know is really I'm describing the motion of all of the points across that object, but just to simplify things, I can make that kind of assumption. So let's do that here for him. For this motion diagram, for each image that I drew, let's put a single point, say at his middle position to represent this guy. Okay, so here it is. I'm using the particle model and I'm reducing him to a single point to try to understand his motion. And now here's another thing to notice with this motion diagram is that I have 1, 2, 3, 4, 5, right? A series of images, a discrete number of images here. When really, like, he was at all positions, right? He didn't teleport from, say, this position to this position. Some time elapsed between this position and this position. So there's something that I'm going to call a delta t. That's a time interval. That's how long, right? How much time advanced between subsequent images in this motion diagram. Okay. And for this to make sense, for us to use this as a physical analysis, the thing that I'm going to tell you here is that software that I use stacks the images with the same delta t between each images. So the time that it takes from him to go from this first point to this second point, maybe let's put some labels on these points here. 0, 1, 2, 3, 4. So the time that it takes for him to go from 0 to 1 is the same amount of time that it took him to get from position 1 to 2 and 2 to 3 and 3 to 4, etc. Now, we can also draw some interesting physical quantities on here using vectors. So I can draw, what is a vector? We're going to talk a little bit more about this as we go along, especially when we come to chapter 3. But a vector is an object that has some directionality in size, and we usually represent it pictorially like an arrow, something like this. So I can draw a vector that starts at one of my point particles here and points to the next one. And I'm going to use an arrow and it's going to point in the direction that time is flowing here. And I can do that for every subsequent position that he takes in this motion diagram. And I get a series of vectors, green vectors, that look like this. These green vectors are what we're going to call displacement vectors. Okay. It's a vector that shows me how his position changed. Okay. So this is a displacement vector. Okay. And you can see that sometimes his displacement vector is larger, like right here in the middle of this jump, he has a very large displacement vector. And up at the beginning, when he's trying to leave the platform, he has a very small displacement vector. Well, what does that tell you? Remember that the delta t, okay, the delta t is the same here. So I can also form this ratio, delta r, the ratio of the displacement vector to that time interval. Okay, and this is what we call the velocity. So in this picture, because the delta t is the same for each subsequent point on this picture, those green displacement arrows are also proportional to the velocity. Okay, this is proportional to v delta t, right? This is like v delta t. Delta t is the same for all of these. So where I have a larger vector here, I know his velocity was higher. He covered more distance per unit time that advanced. Okay, so you can see his velocity was small up here. His velocity was large here. All right. Now we're just talking about using the particle model and simplifying how to describe the position of the person in this image. What do we do about the background here? How do we, what is the simplifying or reduced thing that we could draw to replace the background? Anybody have an idea? If you have an idea, you can either raise your hand and share, or you can throw it into the chat. What's a tool that we can use to be a stand-in for this background that we have here? Any ideas? Okay, excellent. Ricardo said a coordinate system. That's exactly right. So we could imagine drawing some coordinate system here, right? Something like this, and we could say that this is y and this is x. Okay. And that coordinate system, right, we're making all those measurements, all those points. We could describe where those points are with respect to that coordinate system. Okay. That's the same thing. When you're looking at the image, you know he was moving because you see that his position is changing with respect to, say, you know, that bar or some position on the steps. So the mathematical, right, or the simplifying tool we're going to use is define a coordinate system and pin that coordinate system to a fixed position on the background. So the only reason we know that he's moving is because we see a background, we see a reference, and his position is changing with respect to that reference. Right? If he was jumping on a white background, okay, it would be hard to know whether or not he was actually moving or the camera was moving. There would be no reference to really understand what things are moving with respect to one another. Now we would still be able to make this motion shot because like there's a physical object making this recording and the camera is fixed, so it would still record that. But in general, right, you need this fixed coordinate system to understand that there's motion happening. And so once we have a fixed coordinate system like this, we can define a quantity that goes from, say, the origin to each position, and we're going to call this R. This is the position vector. Oops. Okay. The position vector is just a vector that goes from the origin of a coordinate system to the position where some object is in space, right? So for each position, there's a different position vector to represent where the person is, where my son is in this picture. Okay. So that's the general idea. And one other thing we can point out here is that if I take two position vectors, say this is position vector 3, R3, and this is position vector 4, this displacement vector we're going to see is actually the difference between R4 and R3. And we'll come back to that in a second to see that those displacement vectors are just differences in position vectors. All right. So let's look at a few more diagrams here. So here's my son walking across in the room in my basement here. And I took this motion shot of him. And we can do the same thing, right? So now this is a little bit simpler to analyze because we see that he's just moving in one direction. So we can reduce him to a single point here. And we can draw the velocity vectors connecting those points. Okay. And we can see that he's walking across the picture from left to right in this case. Now let's compare two different motions. So above is him walking across the room and below is him also walking across the room. In those two examples, in which case is his velocity larger? Which case is he moving more rapidly? So let's call this image A. Let's call this image B.
If I had to
For those two different motions, which one has the larger velocity? So I'm going to launch a poll. We'll do this periodically as we meet in person. You can provide your response here. I usually give about 30 seconds for you to respond to these polls. There's no penalty for getting it wrong, so this is really just to help you stay engaged and think about the problem. Okay. I'm going to give you about 3 more seconds. We're going to end, and I can share the results with you, and you can see almost everybody selected B here, right? We can draw the points, and we can draw those velocity vectors that connect his, right? And you can see in the lower picture, right, the size of that velocity vector is larger than the length of that vector, that arrow that I drew is larger than the one on the top. And that means the velocity is higher, right? VB is greater than VA. Okay. That means he's covering in the lower picture more distance per time, right? That's why the same amount of time elapsed in these two images, there's fewer images on the bottom because he covers more distance per fixed unit of time. Okay, let's look at this image. What's happening in this image? Is he A, slowing down? Or is he B, speeding up in this image? Let me relaunch the poll. Is he speeding up or slowing down in this picture? Okay, I'm going to go ahead and end the poll because I think we have everybody responding. Everybody said he's speeding up. Okay, here's his position. How do we know he's speeding up? Because his velocity vector is increasing in size as the motion goes on here. He's covering more distance per unit time as this sequence is advancing. What about this one? What would we say is happening in this case? Is he speeding up or slowing down? Let's relaunch the poll. Is he speeding up or slowing down? Let's go with A for speeding up, B for slowing down. Okay, good. Go ahead and stop it. Almost everybody selected that he's slowing down, right? He starts here. His velocity vector then starts shrinking as he goes in this direction. So that's an example of slowing down. That velocity vector, right? The size of the velocity vector. What information is in that velocity vector? There's two things. It's a vector. The size of it tells me the speed, how fast he's moving. The direction tells me in which way he's going. What about this one? What is happening? Can somebody describe this motion? Maybe just take Michael.
He's not speeding up or slowing down. He is staying at constant velocity, just like Addison just said.
Yep, constant velocity. Thank you. I agree with that. So here's his positions. Okay. So it looks like there's equal spacing between those points if we reduce them to a single particle here. How do I draw the velocity vectors here? So notice that I could draw, is this the right answer? Does this look right that the velocity vectors are about equally spaced and pointing in this direction?
No, they're not equally spaced.
They're not perfectly
before-
equally spaced. Yeah. They're not perfectly equally spaced, right? You can see, for instance, at the beginning, it's a little bit smaller than at the end. So there's probably a slight speed up here. Okay. It's not quite as dramatic as in these original images here. Is this the right diagram for this picture? What do people think? So I can tell you this is not the right set of vectors here. What's another choice? Madison?
He could be walking backwards.
Yeah, exactly. In this picture, even though I didn't tell you, I asked him to walk backwards. He was walking backwards for this particular image. Okay. So in this case, the correct answer, right, should be velocity vectors that point in this direction. How do I disambiguate those two cases? How can I put information on this graph so that I would know that he's walking backwards? What would I have to do? Any ideas?
I would probably say you would have to add like a what's it called? A coordinate plane. There we go.
A coordinate
Okay.
what? Sorry, Michael, I didn't catch the
Coordinate-
word.
Coordinate graph
Coordinate
or
system?
plane. Coordinate system. Thank you.
Okay, so let's see if that helps. That's a good idea. So let's draw a coordinate system. Okay. If I draw the coordinate system here, so here's the coordinate system, X, Y, and X, say something like this. Does that help me determine, right? I mean, at each of these, I can describe these positions here. Does that coordinate system help me know whether or not he's moving from left to right or right to left?
No, I think because of the gap between them is reducing from right to left. That is why, I guess.
So what extra information do we need to know about if he's moving right to left?
The distance from the right to the left is reducing.
The distance on the right. Okay, so thank you guys for the ideas, right? So lots of you guys are focusing on, is there information about, right? Is there information in the distances and the positions that can tell me which direction he's going? And the answer is there's not. Positions can't tell me which way he went. What other physical quantity do I need to understand which direction? All right, I'll give you guys a hint. We're going to use the symbol T to represent it, right? The time. The piece that you also need to know to understand the direction is the time. And how can I represent that? Well, if I put an order to these, right? If I told you that this was, say, time 0, and then this was T1, and then this happened at T2, and this happened at T3, and say this was at 0 seconds from when I started shooting, and this was 1 second, and then this was 2 seconds, and then this was 3 seconds. Well, now you can see the order of when the object was at the certain positions. Okay. So in order to understand direction, right, there has to be some velocity. And you can't know about velocity without time. Remember we said on the previous slide that velocity is like a change in position with respect to time, right? If I take a change in position, we're going to see the definition of this change in position is R2 minus R1, where this is the final, right, a position at some later time minus some position at some earlier time. So implicit in this delta R is that you know the sequence, you know when the object was, where it was first and where it was second. Okay. So to really have a complete understanding of these diagrams, you need the particle, you need the coordinate system, and you need to know the sequence, right? The times when the object was at each position. Because if I just gave you something like this, say 3, right, a series of points here, and say I gave you a coordinate system X, and I asked you, what is the motion of this? Well, what you want to do is infer that, right? I mean, it looks like maybe this thing is speeding up or slowing down. You don't know which direction is going unless I label the points. So, right, maybe I could label like 0, 1, 2, 3, 4, and now I know that this thing would be, you know, speeding up as it moves to the right. But I could have labeled these differently, right? This would be the same set of images, right, or the same particle if I relabeled these things. And maybe you could even get, right, wild things. I mean, you could have this be 1, 2, 3, 4, 5, right? I mean, this would be okay. This is, I've skipped 1, didn't I? Let's call this 1. What would this look like? This means the object would be going like here to here, 1 to 2, 2 to 3, and then 3 to 4, and then 4 to 5, right? That would be a picture of an object that went to the right and then turned around and came back to the left. And all those would have those same positions in the coordinate system, right? So it's critical that we know position and time to be able to analyze and understand the motion. Make sense? Okay. Oops. That's not what I wanted to push. Okay. So let's see. Here's a sequence of diagrams of motion and 2 cars, A and B. Let's try this. Which of the 2 cars, let's just make sure we're on the same page here. Which of those 2 cars, assume they're not doing any of the crazy things like we just drew, that they're going in the direction that they're pointing, they're driving down the street, and that the images don't go in some kind of unusual order. Which of the 2 cars is moving more slowly? Remember, how are we going to find if they're moving more slowly? We can reduce the car to a point, try to draw the velocity vectors by connecting the points with an arrow, and the one that has the smaller arrow is going to be moving more slowly. Let me go ahead and share the results here. Most of you selected A, right? If I put the points here and draw this vector, let me get a better crop. I'm drawing with red on red here, right? I get a velocity vector like that. You can see that vector is smaller than this vector. Okay. Now this thing asked about the speed, right? Which car is going slower? Speed is just talking about the size of that velocity vector, not necessarily the direction, right? The direction is is a separate bit of information that's encoded in the velocity. Velocity has both of these things inside of it, direction and speed. Okay, what about this one? So I have 3 motion diagrams on the right-hand side of this plot. One of them is a motion diagram of, say, a speck of dust settling slowly to the floor at a constant speed. One is a ball being dropped from the roof of a building, and one is a rocket ship that's accelerating upwards. Oh, sorry, no, it's not. One is a rocket. Is a rocket ship that's descending slowly to make a soft landing. Sorry, it's a landing rocket ship. Which is the correct diagram to represent those different cases here. So let me stop sharing, let you indicate your choice here. So we have a dust speck falling at a constant speed, a ball being dropped from the roof of the building, and a rocket coming to a gentle landing on Mars. Okay, I'm gonna go ahead and end the poll. Most of you selected B. Okay. Let's check. Let's just draw the velocity vectors. All right, I'm just gonna draw the arrows to connect all these points here on each diagram. And so we can see when I do this that the motion are these velocity vectors on diagram A are increasing as time goes on. Look, the points are labeled, so I know it starts here and it ends here. So in this example, the velocity, the object is speeding up as it falls down. Well, that's not constant speed. That's something that's speeding up. That's not a rocket ship that's slowing down as it descends. So that has to be the ball dropping. Okay, so this is the ball. Here we see that the velocity, right, the length of these vectors is the same between each successive point. So that's constant speed. So this is my dust particle, dust particle falling at a constant speed. And here we see the length of that velocity vector shrinking. And so this has to be the rocket coming to the soft landing on the surface of the planet here. So B is our correct answer. Okay. So real quickly, let's talk about vectors. I hope you guys have seen vectors or remember your vector algebra, but let's just review it really quickly. Those arrows that we were drawing to represent velocity or to represent position or displacement are vector quantities here. And we can do mathematical operations on vectors. So I can take two vectors, say I have vector P and I have vector Q, and I could add them together. How do I add two vectors together? Well, if I have two vectors, say I have vector A and I have vector B, the way I add two vectors together graphically is I take, right, if I want A plus B, I take the two vectors and I put them tip to tail, okay? And that resulting vector, let's say the resulting, oops, I just erased it, right? So I had vector A tip to tail with vector B. There's a resulting vector, right, that spans that length from the tip of vector A to from the tail of vector A to the tip of vector B, that is the vector A plus B. And we're welcome to give it another name. We could call that vector C. And that works even if there's, right, if say my vector A points in this direction and maybe vector B is long and points in this direction. If I want B plus A, what I do is I'm going to put vector A tip to tail with vector B. So I'm going to take vector A and I'm going to put a copy of that vector. Let me see if I can get this and align it with vector B. And then the vector that spans from the tail of my original vector up to the tip of my final vector is that vector sum. Okay. So here's vector C, the sum of those two vectors. So in this instance, here I have two vectors that I've given you, vector P and vector Q, and I want the vector sum of P and Q. Which from A, B, C, D is the vector sum of P and Q? Okay, I'm gonna go ahead and end the poll. Most of you selected A, so let's see how we do it. Here's vector P. We're gonna take and put a copy of vector Q and start its tail at the tip of vector P. And it goes out something like this. And then we're gonna draw the vector that connects the tail of my original vector to the tip of the final vector to get that resulting sum, P plus Q. Okay. And this guy looks like A here. Notice that one other property of these vector sums here, I could also do Q plus P. And vectors, when you add them together, the order doesn't matter, right? So this should be the same as P plus Q. So let's check to make sure it's the same. So here's Q, and now I'm gonna put P tip to tail with that guy. Okay, it looks something like this. Oops. P looks something like this. And if I draw a vector that spans, right, so here's vector P. If I draw the vector that starts at the tail of Q and goes out to the tip of P, again, I get this same vector A as the result. So when you do the vector sum, the order, which vector you put tip to tail with the other one doesn't matter. You get the same resulting vector out. Okay, so you can switch the order between the vector additions. Okay, what about this one? Same vectors P and Q. Now I want to take the vector difference. I want to take vector P minus vector Q. Well, how am I going to do that? Well, if I have a vector, let's remember what properties we need. Say I have a vector A. Vector A minus is just the vector that has the same length but points in the opposite direction. So the only new information we need to know here is that a negative vector points in the right parallel to the original vector but in the opposite direction. And so this one I'm writing, this is the same as vector P plus vector negative Q. Okay. So I could find what's vector negative Q. Vector negative Q is this vector that points in the opposite direction of Q. And now if I want P minus Q, well, I just have to add vector P to vector negative Q. So I'm going to let you do that. Tell me which is the vector that represents P minus Q here. Okay, let me go ahead and end this poll. Most popular answer was D. Some of you selected B as well. So let's see what we do here. So here we just drew together vector negative Q. So in order to find P minus Q, we're going to add together vector P and vector negative Q. Put them tip to tail. Here's negative Q. Now I'm going to find that vector that goes from the tail of vector P out to the tip of the final vector. And that is my P minus Q. So the answer here is D. Okay. So now we're going to think about acceleration. We're going to try to think about a new physical quantity here and use some of our vector algebra here. So we can think about a physical quantity that we're going to call the acceleration. And the acceleration, the average acceleration is going to be delta V, the change in velocity with respect to some time interval here. Okay. So this is going to be vector V, say V2 minus vector V1 divided by delta T. Now, when we're looking at these motion diagrams, remember that delta T is just always some fixed number here. So if I can find the difference in the velocities, the difference in the velocity vectors, that gives me a new vector that we're going to call, right? That's proportional to a new vector if I divide it by the time interval that we're going to call the acceleration. Accelerations tell me how an object's velocity is changing. Okay. So let's try this example. We have a particle that has a velocity v1 that's given in this diagram here, and it accelerates from 1 to 2. What is the velocity vector v2 as it moves away from 2 on its way to point 3? So how are we going to do that? Well, we have v1. Then there's going to be another vector that, right, that I'm going to draw coming off of 2 that are our choices here. And there has to be an acceleration that's associated, right? The acceleration is going to be something like the difference in these velocities. So which one of the vectors on the right, when I take the difference of that vector with the vector on the left, gives me that acceleration vector? Okay, let me go ahead and end the poll. A lot of you selected B. Okay. So let's see what's happening. We've got to find a vector, right? So I already have V1, and I'm going to take V2 minus V1. So what is let's write, so in order to V2 minus V1, we just said this is going to be the same thing as V2 plus negative V1. It's negative V1. What does negative V1 look like? Well, negative V1 looks like this. There's minus V1. So what vector can I add to that V1 to get that vector A? Well, let's see. If I take B, our most popular choice, I'm going to take V1, and I'm going to put it tip to tail with V2. And the result, if I sum those together, is something like this, right? From the tip of the first vector to the, from the tail of the first vector to the tip of the second vector. And that matches this acceleration vector that I see here. Okay. So you're correct. Most of you are correct that the answer here is B. I could also do it in a different way, right? Notice that we're saying that the acceleration times delta t, if I just divide that delta t over, is equal to V2 minus V1. This thing, right, when I draw this on these motion diagrams, this, we don't write it, but there's really this delta t hiding here because I have these even time intervals. And what I can see is that I can get, say, V2 is just going to be equal to V1. If I add V1 to both sides, it's going to be equal to V1 plus A delta t. Right, and so I could have also done this taking V1, adding that acceleration vector to it, and the result is a vector that points down like this, and that has to be V2, and that also matches this vector. Okay. All right. We have about 1 minute left. I think we're going to pause here for today. We will pick up with this tomorrow. So we have a few more, I have a few more problems to go over, just introducing some of this analysis. And then we're going to talk a little bit at the end of class tomorrow about units and significant figures. And then I think you should have all of the tools you need to do the homeworks for chapter 1. Are there any questions over the material we covered today before we stop? So just to remind people, these lectures are recorded and being posted on our section YouTube channel. Yesterday's video has been posted. I try to post them, fairly quickly after class so that they're available for everybody. So if you need to review some of this, please check those out. Otherwise, that's it for today. I will hang around for another 5 minutes if any of you want to ask questions after class time. And then otherwise, I will see you tomorrow. Have a great day, everybody. Thanks so much.
I had a really quick question.
Yeah, go ahead,
Um,
is that Jake.
Yeah, I just wanted to verify that the two things that are due tomorrow by Wednesday are the Slack messages to you